So this video is going to be about motion graphs, specifically graphing uniform acceleration. Very much a review from last year with only a few tweaks to kind of make it more IB. It will be, though, when we get to practice problems, more complex, and that's where we're going to have to delve into how to understand IB motion graphs as opposed to what we did last year, but it's the same concepts. So let's just do this review to go through it and show you the new changes that might throw you off. The first is we have a displacement time graph. You're very comfortable with that. These show things that don't have acceleration, right? It's either going at a constant speed of 0 or a constant negative speed or constant positive speed. So displacement is the distance away from a reference point of the object as measured in meters. So we're measuring it from some reference point. So that means there must be a direction to it. Must be forward, backwards, 70 degrees north of, northwest or something like that. And when that happens, that means it must have a direction and it's a vector. The one thing that might be different is we're using S for displacement. There's really no reason why. It just became the symbol for displacement. And we have the displacement time graph. So as we move down, we have velocity. Again, should be comfortable with. We use the symbol V, the rate of change of displacement per unit time as measured in meters per second. Because it's a rate of change, we know it's a slope of a displacement time graph. We also know that since it's the rate of change of displacement and displacement is a vector, that means that velocity is a vector as well. And we're going to often mention direction. If we're talking about graphs, or we're talking about one-dimensional motion, or even two-dimensional motion sometimes, we're going to look at it as just positive or negative. So this just means positive or negative right now. Right now it's going to mean that. We might at some point in time need to find the component vectors. So like if it's going 30 degrees above the horizontal, what is the vertical component? What is the horizontal component? And that's where we're going to get into two-dimensional motion. But right now, one-dimensional motion, let's keep it simple, positives and negatives. So in order to translate this displacement time graph to a velocity graph, we just need to look at the slope, right? So when we go down, we're looking at slope. And we have a 0 slope for 2 seconds. And then the blue is a -1 slope for 2 seconds. And then the red is a positive 0.5 slope for 2 seconds. And we can connect these if you want with like dotted lines. You don't have to. And that's our velocity time graph. The one thing we did in the extensions is the difference between average velocity, calculated in total displacement covered over a period of time, divided by that amount of time. So a time has to pass for you to be able to find an average velocity because it's an average. You might say, oh, if it's an average velocity, what if I just say, oh, it's 0 plus -1 plus 0.5 divided by 3, and you would end up with a number. And I guess in this case it would work because they all have equal time periods. But if they don't have equal time periods, you can't do that. So I would highly suggest not just averaging the velocities. And I would suggest that you find the total displacement divided by the total time. So if I want to find the average velocity of this, I would think of this displacement time graph, and I would say, what is my total change in displacement? Well, I started right here, and I ended right here. So I would think of my average velocity as this dotted line that's connecting those two. That is my average velocity. And I would find that by taking my total displacement covered, which is -1, right? It went from 1 to 0 in 6 seconds. So my average velocity would be -1 over 6, -1 meters per 6 seconds. And that would be my average velocity. Now, actually, I never so -1/6 meters per second. I don't have a calculator with me right now, but I do not like writing in fraction form. So I would want to write this in decimal form. So this would be your final answer. We don't write in fraction form. And then instantaneous velocity is measured at any moment of time. So you can either calculate it by using kinematics equations, which we experienced in the extensions, or through the tangent of the displacement time graph. But in this case, the displacement time graph doesn't have curves, so the tangents aren't that tough. So it's either you have a instantaneous velocity of 0, -1, or +1/2. That's it. Okay, going to acceleration, and this is what we also did last semester. It's the rate of change of velocity per unit time. So again, we're looking at a slope of a velocity time graph. And since it's a change of velocity per unit time, and velocity is a vector, then acceleration is also a vector. Now in this case, there's no acceleration going on, so we pretty much have a flat zero acceleration. So uniform acceleration, which is what we'll be using for graphing, for calculations, for doing like the kinematics equations. They're either going to be a uniform acceleration of 0 or a uniform acceleration of something that's positive or negative. You're never going to have to deal with changing accelerations in calculations. You might have to deal with it when it comes to like air resistance, like an opposing force that's increasing or decreasing, but it's never going to be based on, you're never going to do mathematical calculations. You're only going to have to analyze the graphs for that. Okay, so this is translating displacement to velocity to acceleration, but more commonly in the more what we started doing in the extensions was translating velocity back to displacement. This is a rather simple graph. So we do know that if we want to go displacement to velocity, we know we want to find the slope. And then if we want to go velocity to acceleration, we want to find the slope. But what about velocity back to displacement, or in the other words, acceleration going to velocity? How do we move that way? And that's because slope, the inverse of the slope is the area under the curve. And when I say area under the curve, I specifically mean until the x-axis. So we have that little area, and then I'll have like this little area, and then I'll have this little area. And so I broke that into 3 areas, and under the curve just means to the x-axis, and that's why I flipped sides between 3 and 4 seconds versus 4 and 6 seconds. So when we go to displacement, I want to see how my displacement is changing. Well, first, we want to identify the points of displacement. In the beginning, we're just going to say we start at 0, unless otherwise noted. Let's keep that black. And for every second, I'm traveling 0.5 meters, as shown by these graphs, right? Like I go 0.5 meters, and another 0.5 meters, and then another 0.5 meters. So I'm going to plot 0.5, 0.5, 0.5, and it should be a straight line, as shown by the constant velocity of the black line. So that's easy. That's an easy line to draw. And then we have a red line. Now, between 3 and 4 seconds, even though the line's going downward, we're still traveling forward. This is like if I was driving at a constant speed up until a red light, and then I pressed my brake and I slowed down, and between 3 and 4 seconds, I slowed down and I stopped. And then for some reason, I decided to go in reverse between 4 and 6 seconds, as shown by the negative. So I'm going to want to include my calculation, my distance changed. So between 3 and 4 seconds, I travel, that looks like, okay, it's a triangle, so it's 1/2 base times height, 1 times 0.5 times 0.5, so it's 0.25. So I would travel, between the 4 seconds, I travel to this point. Positive, right? Because it's a positive change, it's in the positive axis. And then my negative change, I want to do the whole calculation. I could do between 4 and 5 seconds, and then between 5 and 6 seconds, but I think it's just easier if I just did the whole thing. So I would look at 2, it goes over 2, down 1, so it's 2 times 1 times 1/2, because it's a triangle, and that's just -1. So I'm going to go down -1. So I might write here, let's write -1 here, just so I know, and then right here I write positive 0.5, and here obviously is positive 1.5. So if I went down -1 in 2 seconds, well, I'm at 1.75, so I'm going to go down to 0.75 because I only went down 1 in 2 seconds. So I am right here. So, and how does that look? Well, I know that I have curves because my velocity is changing, so there's an acceleration. And I know that at time equals 4 seconds, I am at a 0 velocity, so I should have a horizontal line right here. So I'm going to draw my curve. There's my curve, and that's between 3 and 4 seconds. And then between 4 and 6 seconds, I'm going to curve downward like that. So in order to get from velocity to displacement, I needed the area under the curve. Similarly, that means that to get from a velocity from an acceleration time graph, I would want to also find the area under the curve. And so when you're translating between graphs, the best way to think about this is looking at the units themselves. The area is just the base times height. And in this case, the base is seconds, right? The units are seconds for the base. And the height, well, for acceleration is meters per second squared. So if we were to multiply this seconds would cancel out with this seconds, and we would end up with meters per second, which is a velocity. And that's why if we take the area of an acceleration, we would end up with velocity. And you can translate that and say, well, the area of a velocity graph is meters per second times seconds, which ends up with meters. Similarly, if we take the slope of the line, we would get the rate of change, the division, y over x, which is meters per second. That gets the velocity, and so forth. Now, when we look at this graph, I could look at my displacement time graph and try to identify a instantaneous velocity looking at this. And I said you can either find it through kinematics or on a graph. And graphing is this is a very common technique. So let's say I wanted to find my velocity at 5 seconds and I didn't have my velocity time graph. Well, then I would have to imagine, I would want to take like a straight edge and put it at 5 seconds and try to define the line, like the slope of the line right there, and I would extend it both ways. Now, of course, I would need a straight edge. And then I would need to take the points on this line. So maybe I'd like take this point and I'd take this point, and I would find the slope of that line. So the slope of that line is instantaneous velocity at 5 seconds. Which should be, if I were to do that correctly, should be negative 0.5. Which looks pretty darn close, right? Yeah, because I mean, I'm going through this point as well, and that looks like negative 0.5. So we're looking good. The question I have, though, is using the above graphs, calculate the object's average velocity between 0 and 6 seconds. So using these graphs, which one would you use? And try to find the average velocity. Pause this video, solve it, and I'll have it done as well. All right, so using my graph, I drew, or you can just imagine, an average velocity line of the total change in displacement and the total time. So it went up 0.75 meters in 6 seconds. So my total displacement is 0.75 seconds. I'm sorry, 0.75 meters. And my total time is 6 seconds. Similarly, these symbols, right? If you don't know what this means, this just means total, or like sum, or that's it, just total or sum. And so our average is 0.75 divided by 6, which is 0.125 meters per second. So this review of last year's content is just talking about the definitions of displacement, velocity, acceleration, how to translate between graphs, average velocity, instantaneous velocity, knowing that they are vectors and therefore they have positive or negative direction. So we're going to use positive and negative graphs, knowing how to translate between velocity and displacement graphs and velocity to acceleration graphs, and recognizing how to calculate instantaneous versus average velocity. Now, where we're heading next is can we use these graphs to get to kinematics equations. So that will be where we're heading next. You will be receiving a practice problem to work after this video that you will complete before next class.